Welcome students to online classes of mathematics for class 9th. In this video we're going to study chapter number 10, which is circles of NCERT textbook, and we'll be covering the remaining question of exercise 10.5. okay, this is from the session number 6 for this particular chapter. Myself Deepak Godram, digital mathematics in Kendriya Vidyalaya Sangatam. So let's start with today's class. Here we'll be looking at the subtopics angles subtended by an arc and the cyclic quadrilateral. Okay, based on this we have exercise 10.5. Now let's move to the exercise 10.5. Since we have already done the first 4 questions of the exercise 10.5 in the previous session, okay, so now we're going to start with the question number 5. Question number 5 here is, in figure 10.39, A, B, C and D are 4 points on the circle. So we have these 4 points A, B, C and D which are on the circle, and AC and BD are intersecting at point E such that BEC is equals to 130 degree and ECD is 20 degree. We have to find the value of angle BAC. BAC is given here. So let's start the solution. This is answer number 5. Let's first write the given part. Given here is a circle having 4 points A, B, C and D. A circle having 4 points A, B, C and D, in which AC and BD intersect at point E. Such that we are given two angles, that angle BEC is 130 degree and angle ECD is equals to 20 degree. Okay, what we have to find here is we have to find the value of angle BAC. Let's start a solution. So what we are going to do is, from figure you can see this is forming a linear pair. This angle is given 30 degrees, so this second angle will be of 180 minus 130 degree. Okay, that will be 50 degree. Okay, so we'll write we have, okay, from this figure we have the sum of the angle BEC, sum of angle BEC plus angle DEC will be equals to 180 degree. Okay, BEC is given as 130 degree, so angle DEC will be 180. Okay, that is angle DEC equals to 180 degree minus 130 degree, or DEC will be equals to 50 degree. Okay, now in triangle DEC we have, what we have is, this was the linear pair. Now we are going to apply the angle sum property of triangle for the triangle DEC. Okay, so that is angle BEC, not BEC, angle DEC plus angle ECD plus angle, okay, we are taking angle B is DEC and angle ECD, and the third one will be CDE equals to 180 degree. Okay, this is the angle sum property of triangle. Let's write angle sum property of triangle. Okay, So DEC of calculated, which is 50 degree, ECD is given as 20 degrees, so we have this CDE equals to 180 degree. So this CDE is equals to 180 degree minus 70, so this turn out to be CDE is equals to 110 degree. Okay, and from figure we can write this as CDE can be written as, or this CDE can also be written as angle CDB, so this will also be equals to 180 degree. Okay, so now we can say that since angle BAC and angle CDB are the angles in same segment, therefore angle BAC will be equals to angle CDB will be equals to 110 degree. This is by the theorem 10.9, which says angles in the same segment of a circle are equal, so the value of angle BAC is equals to 110 degree. Okay, so that's the solution of question number 5. Now moving to the next question. Question number 6 is ABCD is a cyclic quadrilateral whose diagonal intersect at E. So we are given a cyclic quadrilateral ABCD whose diagonals are intersecting at point E. If DBC is equal to 70 degree and angle BAC is equal to 30 degree, we have to find the angle BCD, and for the AB equals to BC, we have to find the angle ECD. Okay, so let's first draw its figure. So this is the figure of this question. We have the cyclic quadrilateral ABC in which the two diagonal AC and BD are intersecting at point E, okay, which is here, and we are given the two angle DBC is 70 degree, which is here, and angle BAC is 30 degrees here. Okay, we have to find the two angles. One is BCD is this one, and we have to find this angle BCD, and angle ECD is this one. Okay, this complete angle and this part of this angle. Okay, so we have to find these two. Let's write a solution. This is answer number 6. First we'll write the given part. Given here is a cyclic quadrilateral ABCD, cyclic quadrilateral ABCD whose diagonals are intersecting at point E. Okay, and angle DBC is equal to 70 degree and angle BAC is equals to 30 degree. Okay, we have to find, what we have to find here is we have to find the two angle, that is first is angle BCD and second is angle ECD. Okay, so let's start the solution. First what we're going to do is, since this angle BAC is given as 30 degree, so its corresponding angle BDC will also be equals to 30 degree, because they are the angle on the same segment. Okay, so its solution is this angle BDC will be equals to angle BAC, because these two are the angle in the same segment. Okay, let's try the reason for this one. These are the angles in the same segment. Okay, that's why these two are equal. We are given the angle of BAC, we are given the measure of angle BAC, therefore angle BDC will also be equals to 30 degree. Okay, now what we're going to do is we'll apply the angle sum property in the triangle BDC. Okay, so write in triangle BDC, we have, okay, we are going to apply the angle sum property, that is angle BDC plus angle DBC plus angle BCD will be equals to 180 degree. This is angle sum property of triangle. Angle sum property of triangle. Okay, so we have the angle DBC is, BDC is given as 30 degree, angle DBC is 70 degree, and we have to find the angle BCD here, which is 1 equals to 180 degree. Okay, so angle BCD from here will be 180 degree. This 30 plus 70 is 100, that will come here. So angle BCD will be equals to 80 degree. Okay, so what we got is this complete angle BCD, which we have to find, is 80 degree. Okay, now we are going to find the second angle, that is, in the question it says that AB and BC are equal. That means these two sides AB and BC are equal, and we know that the angles opposite to the equal sides are equal. Okay, so we'll write, since AB equals to BC, therefore their opposite angle, that is angle BCA, will be equals to angle BAC. Okay, reason for this one is angles opposite to the equal side of a triangle are equal. That is, angles opposite to the equal sides of triangle are equal. Okay, so that's why these two angles are equal. We are given the value of angle BAC, that means angle BCA will be equals to, this is given as 30 degree, so this will also be equals to 30 degree. Okay, so now we can write, now angle ECD will be equals to the angle BCD minus angle BCE. Okay, if we subtract BCE from BCD, we'll get the angle ECD. BCD is known to us, which is 80 degree, and BEC is also known to us, that is 30 degree. Okay, so that means angle ECD is equals to 50 degree. Okay, so we got the measure of both the angle BCD and ECD. BCD is here 80 degree and ECD is 50 degree. Okay, now moving to the next one, question number 7 here is, if the diagonals of a cyclic quadrilateral are the diameter of the circle through the vertices of the quadrilateral. Okay, it means we have the diagonals of the cyclic quadrilateral are the diameter, that means the both the diagonals are passing through the center. Okay, prove that it is a rectangle. Okay, so let's first draw its figure. So that's the figure for this question. We have this cyclic quadrilateral ABC and CD, in which the diagonal AC and BD are intersecting at the center O. That means they are the diameter of this circle. Okay, and we have to prove that this cyclic quadrilateral is a rectangle. Okay, for that we are going to prove that the diagonal of this rectangle, or you can say quadrilateral, is equal, then it will be a rectangle. Okay, so let's start its answer number 7. First we are going to write the given part. Given here is a cyclic quadrilateral ABCD. Given is a cyclic quadrilateral ABCD, in which the diagonal AC and BD, in which diagonals AC and BD are the diameters of circle. Okay, so these two are the diameter of the circle, that means they are passing through the center. What we have to prove here is that ABCD is a rectangle. ABCD is a rectangle. This is what we have to prove. Proof for this one is, see, what we are going to do is we are going to prove that the two diagonals are equal. With that, this will be a rectangle. Okay, so let's write, since all the radii is the plural of radius of a circle are equal, that is we have this OA equals to OB equals to OC equals to OD. That means all the four radius, this OA, OB, OC and OD are equal. Okay, or we can write, therefore, or you can say, yeah, this implies that OA is equals to OC, so these two also will also be equal, and this will be half of AC. Similarly, OB will be equals to OD, and this will be half of BD. Okay, this will gives us that the two diagonal, let's name it equation number 1 and 2, equation 1, equation 2. So we can say from equation 1 and 2 we get the diagonal AC is equals to BD, hence ABCD is a rectangle. Okay, we know that in a rectangle the length of the diagonal is equal. Since the length of the diagonal is equal, so this quadrilateral can be a rectangle. Okay, that's the solution for the question. The question number 8 is, if the non-parallel sides of a trapezium are equal, prove that it is a cyclic. Okay, so that means we are given a trapezium whose non-parallel sides are equal, and we have to prove that this trapezium is a parallel cyclic trapezium. Okay, so let's first draw this figure. Okay, so this is the figure for this question. We have the trapezium which is inscribed in the circle. Okay, all the 4 points of the trapezium are on the circle. We have to prove that if its non-parallel sides are equal, that means these two sides DA and CD, if they are equal, then we have to prove that it is a cyclic trapezium. Okay, so let's start the answer. Number 8. First we will write the given part. Given here is a trapezium okay, given is a trapezium, let's say A, B, C, D, whose non-parallel sides are equal, that is we have this DA and CB equal. Okay, you can say that is AD is equals to BC. So this is what given to us. Okay, what we have to prove is we have to prove that ABCD is a cyclic trapezium. ABCD is a cyclic trapezium. Okay, let's start this proof. First we are going to do some construction. Construction here is we will draw two perpendicular DE and CF. Okay, construction is draw DE, which is perpendicular on AB, and CF, which is also perpendicular to AB. Okay, now let's start this proof. So in order to prove that this trapezium is cyclic, what we're going to do is we will prove the one pair of its opposite angle is equals to 180 degree. Okay, so if we prove that the one pair of opposite angle, either pair of opposite angle is 180 degree, then it will be a cyclic quadrilateral. Okay, cyclic trapezium. Okay, so let's start with these two triangle. Okay, ADE and BCF. Okay, let's start this proof. In triangle TEA and triangle CFB, we have, what we're going to do is we are going to prove that these two triangles are congruent by Rhs Congruence Rule. Okay, so let's write. First we have that AD is equals to BC. This is given to us. Then we have angle DEA is equals to angle CFB. Each angle is of 90 degree. Okay, each of 90 degree. Then we have, and DE is equals to CF. Okay, DE and CF are equal because they are the perpendicular between the parallel lines. Okay, so we can say these are the perpendicular between parallel lines. Okay, if the lines are parallel, they have to be equal. So we got right angle, hypotenuse, and side. Okay, so by Rhs Congruence Rule. Okay, so right, therefore triangle DEA is congruent to triangle CFB. Okay, this is by Rhs Congruence Rule. This implies that first is that this angle A is equals to angle B. Okay, that is angle A is equals to angle B. Okay, this is by CPCT. Okay, also this other angle, that is ADE and BCF, they are also equal. Okay, ADE is equals to angle BCF. This is also by CPCT. Since these two triangles are congruent, so the corresponding angle A and angle B are equal. Similarly, this ADE and BCF are also equal. Okay, now we are going to continue with this. Okay, so we have this angle ADE is equals to angle BCF. So what we are going to do is we are going to add 90 degree to both sides of this equation. Okay, so we have 90 degree plus angle ADE. Okay, again we have BCF and we are adding 90 degree. Okay, so as we are adding the equal numbers on the both sides, so equation remain unchanged. Okay, so now this 90 degree here means we can replace this 90 degree by the angle EDC, this one. Okay, similarly on this side, then we can replace it by angle FCD. Okay, let's write this first 90 degree as angle EDC. Then we have already ADE. On the other side we have BCF, and this 90 degree will replace by FCD. Okay, now when we add these two angles, we will get the result as angle ADC. Okay, and after adding these two angles, we'll get the result as angle BCD. That means these two angles are also equal, or we can write this as angle D is equals to angle C. Okay, so let's name this previous equation. We have proved that these A and B are equal, and here we have proved C and D are equal. Okay, now we'll apply the angle sum property for this quadrilateral. Okay, so we'll write in trapezium ABCD, we have that angle A plus angle B plus angle C plus angle D will be equals to 360 degree. This is the angle sum property of a quadrilateral. Okay, for any quadrilateral, the sum for angle is 360 degree. Now in equation 1 we have proved that these two A and B are equal, and in equation 2 we have proved that the C and D are equal. Okay, so what we can do here is we can replace this A by angle B, so this will be angle B plus angle B. Okay, similarly we can replace this C by angle D, since they are equal, so this will be angle D equals to 360 degree. Okay, this will give us twice of angle B plus twice of angle D equals to 360 degree, or from here twice, so angle B plus angle D will be equals to 360 degree divided by 2 equals to 180 degree. Okay, that means the sum of these two angles is equals to 180 degree, which are the B and D are the opposite angle. Okay, we can write hence ABCD is a cyclic trapezium. Since we have proved that the one pair of opposite angle is equals to 180 degree, that means this is one property of a cyclic quadrilateral, that either pair of opposite angle, if the either pair of opposite angle is 180 degree, then it will be a cyclic trapezium. In this case we have this as B and D. We have proved that their sum is equals to 180 degree, therefore this trapezium will be a cyclic trapezium. Okay, so that's the answer for the question number 8. Now moving to the next one, we have the question number 9. This is a very simple question. Question is, we are given this figure. We have two circles intersecting at 2 points B and C. We have these two circles, they are intersecting at point B and point C. Okay, and through B, two line segments ABD and PBQ. We have two line segments which are this ABD and second one is PBQ, this one. So we have two line segments and they are intersecting the circles at point A, D and P, Q, okay, respectively. We have to prove that the angle ACP, which is this one, ACP is here, is equals to angle QCD, which is here. Okay, so question is, we have two circles, they are intersecting each other at 2 point A and B and C. Those 2 points are B and C. Then we have two lines ABD and PBQ, they are intersecting the two circles at point AD and PQ. We have to prove that these two angles are equal. Okay, so what we are going to do is, we'll use the two properties here. First, that the angles in the same segment are equal and the vertically opposite angles are equal. Okay, so by these two properties we can prove that the given angles are equal. Okay, so let's first start by writing its answer. Number 9, we'll first mention the given part. given here is two circles intersecting at 2 point B and C. We have two circles intersecting at 2 points B and C, and through B there are two lines ABD and PBQ intersecting circles at points A, D, P and Q. What we have to prove? We have to prove that the angle ACP is equals to angle QCD. Okay, let's start this proof. First, we know that the angle in the same segment of a circle are equal. So we'll write, since we have two pairs of angle, first is angle, since angle ACP and angle ABP are the angles in the same segment. That means they are the two angles in the same part of the circle, same segment. Okay, therefore angle ACP will be equals to angle ABP. Okay, this is by the theorem. This is, I think, by the theorem 10.9. okay, which says angles in the same segment of a circle are equal. So let's name it equation number 1. Now we'll write similarly. Now the other two angle, that is angle QCD and angle QBD. Similarly, angle QCD and angle QBD are the angles in the same segment of circle. Therefore they will also be equal, that is QCD is equals to angle QBD. Let's name it equation number 2, and reason for this one is again the theorem 10.9, which says angle in the same segment of a circle are equal. So angle ACP is equals to ABP and angle QCD is equals to angle QBD. Okay, now in the figure, if you look at this here, these two lines are intersecting each other at point B and they are forming this pair of vertically opposite angle, and we know that each pair of when two lines intersect each other, each pair of vertically opposite angle is equal. Okay, so we'll write, since line ABD and PBQ are intersecting at point P, therefore the angles, we have one pair of vertically opposite angle, that is angle ABP will be equals to angle QBD, because they are the vertically opposite angles. Okay, let's name it equation number 3. Now from by comparing all three equation, you can see that this ACP is equals to ABP, and ABP is equals to QBD, and this QBD is equals to QCD. That means these all six angles are equals to one another. Okay, so we can write from equation 1, 2 and 3, from equation 1, equation 2 and equation 3, we get that angle ACP is equals to angle QCD. Okay, and this is what we were asked to prove here. Okay, so that's the solution for question number 10 is, if circles are drawn taking two sides of a triangle as diameter. Okay, so we have a triangle whose two sides are taken as the diameter and the two circles have been drawn. Prove that the point of the intersection of the two circles lie on the third side. Okay, this means that suppose if we have this triangle, and by taking this side as the diameter, we can draw a circle here and we can draw a circle here. Okay, like this. Then the point of intersection of the two circles must lie on the third side. Okay, that's what we have to prove here. Okay, let's draw this diagram first. So this is a figure for this question. We have this triangle ABC whose this side AC and AB are taken as a diameter to draw two circles. Okay, and they are intersecting at a point. We have to prove that this point D is lying on the side BC. Okay, so let's start its answer number 10. First we'll write the given part. Given here is a triangle ABC, a triangle ABC whose two sides, let's take those sides as AB and AC, are taken as diameter to draw two circles. Okay, what we have to prove? We have to prove that the point of intersection of the circle lie on the third side. The point of intersection of two circles lie on third side. Okay, so let's start this proof. Before starting the proof, we'll do one construction. That construction is to join this AD. Okay, we have to join this AD. Construction is join A and D. Now what we are going to do is we will prove that these two angles ADB and ADC are forming linear pair. Okay, so let's start its proof. By proving that they are forming linear pair, that means point D is lying on the line BC. Okay, so let's start. So we have since AB and AC are the diameters of the two circles, therefore angle ADB will be of 90 degree. Okay, also angle ADC will be of 90 degree. Okay, this ADB and ADC will form the 90 degree angle, because this angle here is of 180 degree, which is in the center, so its angle on the remaining part of circle will be of 90 degree. Similarly, the angle here is of 180 degree and this will be of 90 degree. Okay, so we got ABD and ADC each equals to 90 degree. Okay, or we can say the angle in the semicircle is always 90 degree. Okay, keep this in mind, the angle in the semicircle is always equals to 90 degree. Okay, now we can add these two. Let's name it 1 and 2. On adding equation 1 and equation 2, we get, what we get is that angle ADB plus angle ADC is equals to 90 plus 90 equals to 180 degree. Okay, this implies since their sum is 180 degree, that means they are forming linear pair. So this implies BDC is a straight line. Okay, so BCD is a straight line, hence D lies on PC. This is what we have to prove, that the point of intersection of the two circle is lying on the third side. Okay, so that's the solution for the question number 10. Now let's move to the next question, which is question number 11. It says ABC and ADC are two right triangle with common hypotenuse AC. Prove that CAD is equals to CBD. So we have two right triangles ABC and ADC with their common hypotenuse AC. You have to prove that these two angles are equal. Okay, so let's first draw this figure. So this is a figure for this question, that is we have these two right triangle ABD and ADC. Okay, and with their common hypotenuse is this AC. We need to prove that the two angle which are angle CAD and angle CBD, we have to prove that these two angles are equal. Okay, so let's start this proof. Answer number 11. First we'll write the given part. Given here is two right triangle ABC and ADC, two right triangles ABC and ADC with common hypotenuse AC. We have to prove that angle CAD is equals to angle CBD. Okay, we'll start with the construction. That construction here is, we will join BD. Okay, join B and D. Okay, let's start this proof now. This is very simple. See here, considering this chord DC, or you can say CD, this chord CD is making two angles which are angle D, or you can say CAD and CBD, which are in the same segment. Okay, so we'll write, since chord CD is making two angles, that is CAD and angle CBD, in the same segment, of circle. Simply, therefore these two angles will be equal because they are the angles in the same segment, which are, we know they are equal. This is theorem 10.9. You will write the statement of the theorem here, that is angles in the same segment of a circle are equal. So we have proved that these two angles are equal. This is by simply using the theorem 10.9. okay, so that's the solution for the question number 11. Now moving to the next question. The question number 12 is prove that a cyclic parallelogram is a rectangle. That means we are given a cyclic parallelogram and we have to prove that it's a rectangle. Okay, we know that in a parallelogram opposite pair of angle is equal, while in rectangle the all angle are of 90 degree. Okay, so if we prove that the opposite, it's already given that in a parallelogram we know that opposite angles are of equal measure, and will prove that their measure is 90 degree. Figure for this one, we have this parallelogram inscribed in a circle, that is cyclic parallelogram. We need to prove that it's a rectangle. Okay, so let's start the answer number 12. First we'll mention the given part. Given is a cyclic quadrilateral cyclic parallelogram ABCD. A cyclic parallelogram ABCD. Okay, this is what given to us. We have to prove that ABCD is a rectangle. ABCD is a rectangle. Okay, let's start this proof. The proof is since ABCD is parallelogram, therefore its each pair of opposites angle will be equal, that is angle A plus angle C will be equals to 180 degree. This is as ABCD is a cyclic parallelogram. Okay, and we can say also angle A will be equals to angle C. This is because ABCD is a cyclic parallelogram. ABCD is cyclic. Okay, so any parallelogram or a quadrilateral, if it is cyclic, that means its pair of opposite angle will be equals to 180 degree. And since ABCD is a parallelogram, therefore opposite pair of angle will be equal. Okay, this implies angle A equals to angle C equals to 90 degree. Okay, because they are equal and their sum is equal to 180 degree, that means each will be of 90 degree. Okay, and so we have proved that the one pair of its opposite angle is 90 degree, that means other two angle will also be of 90 degree. Okay, so we can write similarly, so we can write therefore each angle of ABCD is of 90 degree, hence ABCD is a rectangle. Okay, so we have proved the property of rectangle, that all the angles are of 90 degree, hence this parallelogram ABCD is a rectangle. Okay, so that's the solution for the question number 12. With this we have completed all the questions of exercise 10.5 and we have concluded the chapter 10. Okay, I hope you understood the questions. Now you can practice all this question multiple times so that you can understand better. Okay, so that's all for now everyone.